So good morning, everyone. You guys have any questions about the midterm? Was it okay? Any comments? Was it long or was it Friday, right? It's Friday. Unless you wanted to write more on the theoretical method, I guess. Otherwise, I would think one day would be enough. A few hours, actually. Okay? So, what we talked about last time was we introduced one type of element, the constant strain triangle. And as the name implies, this triangle can only have constant strain, which means it's a very good element if you want to model an object under constant strain. So if this is a homogeneous material and you model under this load, this part will be under constant strain, so I can basically use just two elements and I'll be fine. The constant strain triangle deforms such that it keeps its sides straight. So if this is the original shape, after deformation, it has to keep its sides straight. So the deformed shape of a constant strain triangle looks like this. It just keeps all its sides straight, and you have epsilon 1 will be equal to constant, epsilon 2 will be equal to constant, and epsilon 2 will be equal to constant. And the relationship between epsilon 1, epsilon 2, epsilon 2, and the three displacements, so epsilon 1, epsilon 2, will be described by matrix B, which is the partial derivatives of the shape functions with respect to the positions, multiplied by the 6 degrees of freedom. So the next element that we are going to study is the nonlinear version of this element. So the nonlinear version of this element is called linear strain triangle, and as the name implies, it is able to model a linear strain. So how can this element deform, or how many nodes does it have? So this is the constant strain triangle. If you add mid-side nodes, it becomes the linear strain triangle, and it can deform such that it has a shape like this. The sides would curve. So it allows you for better meshing. So the number of degrees of freedom for this are equal to 12. I have 6 nodes multiplied by 2 degrees of freedom per node. So this is equal to 12 degrees of freedom. The shape functions can be obtained using different ways. The shape functions n1, n2, n3, n4, n5, and 6, according to the 6 nodes, can be obtained by first assuming that the displacement of the element follows the following form. The displacement across the element is equal to a1 plus a2x1 plus a3x2 plus a4x1 squared plus a5x1x2 plus a6x2 squared. So this is the horizontal displacement across the element. The vertical displacement across the element is these same function but different constants. These constants A1, A2, A3, A4, A5, A6 are the generalized degrees of freedom. These are the degrees of freedom of the element. If you give me those numbers, I can tell you the displacement and the strain and everything inside that element. But we can replace those generalized degrees of freedom with these specified degrees of freedom which tell me the displacement and the nodes by simply solving an equation and saying u at node 1 is equal to u1, u at node 2 is equal to u2, and so on. And so A1 up to A6 can then be replaced with the degrees of freedom U1 up to U6, and B1 up to B6 can also be replaced by V1 up to V6. So this is one way of finding the shape functions, and now I can write U is equal to U sum, or is equal to U1 multiplied by N1 plus U2 multiplied by N2, and so on, up to U6 and 6. And V is equal to V1 N1 plus V2 N2 plus all the way up to V6 and 6. But it was also realized that these shape functions can be obtained in a more intuitive manner as follows. So how can I find those shape functions? So I'm going to go back to the element. So I have, this is node 1, node 2, node 3, node 4, node 5, node 6. The requirement for, let's say, N4, the requirement for N4 is that N4 is equal to 1 at node 4. And N4 is equal to 0 at all the other nodes. N4 is equal to 1 at node 4, and N4 is equal to 0 at all the other nodes, which means if this is the element, n4 has it's equal to 1 here and 0 everywhere else. So this is the distribution of n4 over the triangle. So in this case, n4 can be written as the multiplication of those three the multiplication actually of x1, which is this line, and this line, which is 1 minus x2 minus x1, and it has to be divided by a constant, and this constant can be obtained by setting n4 is equal to 1 at node 4. And so if you look at n4 is equal to this, 4x1, 1 minus x1 minus x2. And this constant ensures that when you put x1 and x2 to be equal to the coordinates of this point, n4 will be equal to 1. For n1, for n1, the distribution of n1 over the element looks like this. This is the element. n1 is equal to 1 at node 1, and it's equal to 0 at all the other nodes. So n1 is equal to So n1 would be one of these nodes, and would be 0 at all the other nodes. And so n1 is realized as the multiplication of this line, which is x2, this line and this line. So 1 minus x2 minus x1 multiplied by half minus x2 minus x1 divided by a constant, and this constant can be obtained by setting n1 equal to 1 at node 1. So you end up with n1, which has the following form. n1 is equal to 2, 1 minus x1 minus x2, multiplied by half, minus x1 minus x2. And the rest can be obtained the same. n3, for example. I want a function that will give me 1 here and 0 at these other nodes. So n3 will be equal to this line, which is half minus x2, multiplied by this line, which is x2 equals 0. So let's look at n3. x2 and half minus x2, or x2 minus half, and a constant. The constant can be obtained by setting n3 is equal to 1 at node 3. And this ensures that n3 will be equal to 0 at all the other nodes. So the nice thing about this element is the following. Let's look at the general form. U is equal to a1 plus a2x1 plus a3x2 plus a4x1 squared, and so on. And let's see what is the shape of epsilon 11, or epsilon xn. Epsilon 11 is equal to partial u1, which is the horizontal displacement, with respect to x1. Partial u with respect to x1 will be equal to a2. I can model constant strain plus 2a4 x1. I can even model linear strain in this direction plus a5 x2. I can even model bending. So I can, what this tells me is that this element, if I have the right number of, the right values for the constants, I can model constant strain. If this element is under constant strain, then A2 will have a value. If this element is under bending, so that it has a linear strain along x2, so for example, if this element is like this, and I apply bending on it, then it's able to model a linear strain in the direction of x2. So it's able to model bending strain, and it's also able to model a linear strain in the x1 direction. Which means, if I have a beam, and I apply a load here, for example, or bending load, the closed form solution using beam assumes that this, so closed form solution of this order Bernoulli beam assumes that strains, or that E11 is linear in x2, the strain is linear, the distribution of the strain is linear in x2, linear in this direction. And so one element would be enough for me across the thickness to obtain a solution that is equivalent to the Euler Bernoulli solution, because this beam, this element is able to model this linear strain. Now compare with the previous element. The previous element can only model constant strain. What does it mean that it can only model constant strain? matrix element, if this is the distribution of the strain, epsilon 1, the constant strain triangle can only model a constant strain, which means I have to discretize this strain into constant values. So for me to approximate the triangular or the linear shape of epsilon 1, I'm going to have to come up with triangles like this, which means I'm going to have to make many triangles to be able to achieve an approximation that is as good as the Euler-Bernoulli, because the constant strain triangle I can only achieve constant strain across the triangle. So many triangles are needed to model the linear variation of epsilon 1 across the height. So, in order to form the equations of the of this triangle, the stiffness matrix is obtained by B transpose, by taking the B matrix transpose CivE integrated over the volume, and this is multiplied by the vector U E degrees of freedom of the system. This is equal to the loading or the nodal degrees of freedom of the element, and the nodal degrees of freedom, the nodal forces are obtained as follows. The nodal forces are obtained for a distributed load. It's N transpose rho B integrated over the volume, where B is a vector B1, B2, and the nodal forces due to the traction vectors is equal to Nt multiplied by Tn integrated over the surface, where Tn will be equal to T1 and T2. So basically, what we're saying is, if I have a distributed load or distributed body force that has component rho B1 and rho B2 acting on this element, and let's say rho B1 and rho B2 are constant, and so the total horizontal component would be rho B1 multiplied by the area, the total vertical component is rho B2 multiplied by the area. Now I want to take that total load that's being applied on the element and make it into nodal forces applied on the nodes. So the equivalent nodal forces would be equal to N transpose rho B dV. So basically, if I want to find the equivalent, F equivalent 1, F equivalent 1 will be equal to the integral of N1 multiplied by rho B1 integrated over the volume of the element. The vertical force, F equivalent 2, will be equal to the integral N2, sorry, it's still N1 multiplied by rho V2 integrated over the volume. And so the force at each node is the integral of the shape function of this node multiplied by rho V1, rho V2, or depending on if I'm looking at the vertical component or the horizontal component. Now similarly, if I have a distributed load on the surface, this is the force per unit area of the element. What I'm interested in is I want to take that total load and convert it into forces on the nodes. The equation to convert those forces to the total load into forces on the nodes is obtained by this equation. The integral of L transpose Tn integrated over the surface. So for example, if I want to get this force, this is equal to the integral. What's the node? I think this is node 3. So N3 multiplied by T1 integrated over the surface, where the surface is equal to T dx2, where T is the thickness of the element and dx2 is because we're only integrating on the surface. That's where T is applied. T1 is the horizontal component. T is the element thickness. ds is dx2, integrated from 0 to L. Where this is now. So it turns out if you have a distributed load or a distributed body force, all you have to do is just divide it into equal components on the mid-side nodes, and the nodes on the edges, the vertices of the element, take 0 forces. And if you have a distributed load on an element, then its distribution, as normal form says, is according to the numbers that you see in front of you. So if this is T1, T1 over 6, T1 over 6, and 2 T1 over 3. So this is the distribution. The next element that we are going to study is called the we're going to look at the quadrilateral elements. So the first one is the bilinear quadrilateral 4-node plane element. So for the 4-node plane element looks like this, and it deforms such that its sides stay straight. So once it deforms, it can only take shapes of this form. So you're limited to whatever object that you're deforming. When you use those elements, you're limited that the only way it can deform is such that it keeps its sides straight. It has 8 degrees of freedom, 4 nodes, 2 degrees of freedom per node. The shape function, so u, the horizontal displacement and the vertical displacement. The horizontal displacement is equal to n1 u1, n2 u2, n3 u3, n4 u4. And the vertical displacement is equal to n1 v1, n2 v2, n3 v3, n4 v4. This is the matrix n. This is the vector of unknown displacements or the degrees of freedom of the structure of the element. The generalized degrees of freedom of the element are these functions, or these constants, a1, a2, a3, a4, and b1, b2, b3, and b4. So again, similar to what we talked about, you can find Ni by solving the sets, or the set of equations u at node 1 is equal to u1, u at node 2 is equal to u2, and so on. And so you can replace a1 through a4 can be replaced with u1 through u4. So instead of the degree of freedom being just those general numbers that don't have a physical meaning to the problem, I can replace a1 through a4 with degrees of freedom that have a physical meaning, being the displacements of the horizontal displacements of the nodes. Now this procedure is also equivalent to obtaining the shape functions as follows. I'm looking for a function. Let's look at n1. I'm looking for a function that will give me 1 here and 0 everywhere else. So n1 will be equal to multiplying those two lines, or the equations of those two lines by each other. The equation of this line is equal to b minus x2. The equation of this line is equal to a minus x1. We multiply b minus x2 multiplied by a minus x1 and divide by a constant. This constant, just to normalize it, because I want n1 to be equal to 1 at node 1. So by setting n1 equal to 1 at node 1, node 1 has coordinates negative a and negative b. By putting here negative a, negative b, I can find the value of the constant, and the constant turns out to be 4ab. So indeed, if you put negative a, negative b, you're going to get n1. So negative a, negative b, you're going to get 1. If you put any other node, you're going to get 0. So now let's look at the behavior of this element. So the strain E epsilon 1, epsilon 2, gamma 2 is equal to a matrix B obtained by the differentiation of the shape functions with respect to the coordinates multiplied by the degrees of freedom vector. Now this element is perhaps used in most applications, but it has a problem under bend. So if you use this element with a fine mesh, you're always okay. So this element works really well with a fine mesh. But it has a problem when I'm try to model bending. So if I put this element here, and I'm trying to model the bending of a beam. Now you guys did this. What did you find? What happened when you put one element? You did this for the last assignment. What happened when you used one element?
No good. No good.
So, no good. What happened? Was it too high or too low, the displacement? Do you remember? Okay, what's the real? So what happened when you used only one? So what was the final displacement? 25 millimeters, something like that? 2.4. 2.5.
0.05 units.
Oh, so 0.05 is the displacement. Now what happened when you used one element? Was it 0.1 or was it 0.01? Well, that was the purpose of the assignment.
I think I got like 0.3 actually.
Higher?
For which Poisson ratio?
No,
Or 0.03 or something.
0.03. So for one element?
Yeah, for the which Poisson ratio?
Plus one, yeah. So what you need to know is that, or what's important, what you should have noticed is the following. If this is the exact solution, you're approaching the solution from below. And this is what you should have noticed from your assignment. That as you increase, so this is the measure refinement, and this is the displacement. As you increase the number of elements, your structure at the beginning is very stiff. It cannot deform a lot. It gives you a very small displacement when you're trying to get 0.5. Let's say you get 0.1. If you use only one element. The greater the number of elements, the closer you are to that solution, in particular for this particular type of element. So, now why is that? Now this is not necessarily true for every case, because if I'm trying to model, for example, let's just diverge for a minute. If I'm trying to model this type of loading, mesh refinement will not really do anything, because the exact solution will be the first solution I get. Because the element, whatever displacement of this beam is within the capabilities of this element. So one element is enough. Whatever, if this is one element, or 100 elements, you really will not achieve better results. So, so you really have to see when somebody is doing finite element analysis and giving you a really, really fine mesh, do they really need that fine mesh or not? So for this particular problem, I don't really need a fine mesh. One element will do the whole trick. But for this problem, the deformation is different. What I'm trying to model, this behavior using this possible behavior. Because the element that I'm using cannot model this deformation, I cannot use one element to try and model this curved displacement. Because when this beam curves, you get, or when this beam deforms, you get this, it has this curve. But the element that I'm using can only deform and keep its lines straight. And because of that, we call, and that's why it's stiff. It really, it stiffens up, and when you try to load it, you, in order to achieve this nonlinear displacement, you need, I don't know, maybe 4 elements the thickness that was good enough. So 4 elements was good enough probably. Now this behavior is called the shear lock. Now the reason why it's called shear locking is because of the following. So let's look at the displacement or the possible displacement shape. I'm going just to look at this and this. And try to find what epsilon 1 is. So I did it in a different way in the book. So you can take a look on how I did it in the book. But you can, let's try to find epsilon 1. It's partial u by partial x1. Epsilon 1 will be equal to a2, or I can model constant straight, plus a4 x2. So what does this mean? Well, I should be able to model linear straight. So I should be able to model bending. Okay, let's see what happens now. What's gamma on 2? Gamma on 2 is equal to partial u by partial x1. Partial u by partial x2 plus partial v by partial x1. Partial u by partial x2 will be equal to the following. A3, I can model constant shear, plus A4 x1, plus other terms. So what do you notice here? That any bending, if A4 is not 0, if I have any value for A4, the element will have to exhibit shear, a compounding shear strain. So there has to be some, whenever you try to model pure bending, the element will see some shear strain. So basically you're punishing the element for bending by saying, okay, well, you also have shear strain with every time you model bending. And so by making the element feel that there's extra shear, you're constricting the possibilities of deformation of the element. So this is what is referred to as parasitic shear strain that just appears with bending. It's called parasitic shear, or also called shear lock. The element exhibits shear lock. To find the nodal loads, this will be straightforward when the load, when the distributed load is constant. This is the, if I have a body force pulling the elements, I would like to distribute that body force into forces on the nodes. The forces on the nodes, or the force vectors on the nodes, will be equal to this matrix N transpose multiplied by rho B integrated over the volume, where B is a vector that's made out of B1 and B2. So these are nodal forces due to body forces. And the nodal forces due to traction vectors will be equal to the N transpose Tn integrated over the surface. You take that force per unit area on the surface and you integrate it over the surface and you multiply by N transpose Tn here will be equal to the two components, the horizontal component and the vertical component. And these are two examples. If I have a distributed load that has component T1 and T2 on this side, then it's equally distributed on the two nodes. And if I have a uniform body force acting on the elements, it's uniformly distributed over the nodes. The non-linear version of the quadrilateral element is the quadratic quadrilateral 8-node plane element, and this element is made by introducing 4 mid-side nodes so the element can be formed as follows. So obviously you can have curved sides, so the bending of the beam can obviously be modeled. For this element, the displacement U and V are given according to the following equations. So you can see they have many terms, and you can model, if you calculate epsilon 1, epsilon 2, and gamma on 2, you can find that you can model many sorts of forms of strains, constant strains, linear strains in both directions. And these are the generalized degrees of freedom. These generalized degrees of freedom can be replaced by degrees of freedom that has a physical meaning, and the physical meaning is the nodes of the element, the displacements of the nodes of the element. So A1 up to A8, I can replace them with U1 up to U8, and B1 up to B8, I can replace them with B1 up to B8. And the shape functions can be obtained in that manner, or you can find the shape functions for this particular element by, for example, N1. I want the function that will give me 1 here and 0 at the other nodes. And so this is the function N1 will be equal to this line, multiplied by this line, multiplied by this line. And the equations are, this line is B minus x2. This line is A minus x1. And this line is 1 plus x1 over A plus x2 over B. And so N1 is equal to B minus x2, A minus x1, 1 plus x1 over A plus x2 over B. I need a constant for normalization so that N1 is equal to 1 when x, so N1 is equal to 1 at x1 equal to negative A and x2 equal to negative B. At this point, if this is the coordinate, the center of the coordinates, I want N1 to be equal to 1 when I substitute the coordinates of node 1. So this is for N1, N and N2 and N3 and N4 can be obtained similarly. N5, which is this node, N5 is equivalent to saying I want a function that gives me 1 here and 0 everywhere else. N5 will be equal to this line multiplied by this line. The equation of those three lines multiplied by each other. Line 1, 2, 3. The equations of those three lines are A minus x1, B minus x2, and A plus x1. Again, divided by a constant for normalization, because I want N1 to be equal to 1 at this node and 0 everywhere else. So N5 will have this form. And these are the shape functions that are used to describe the deformation of this element. Now, this element is really useful to model many applications. It just has a lot of degrees of freedom. It has 8 nodes, 16 degrees of freedom. The one thing, if you ever model this element, if you actually model this element, or by model this element, if you actually ever program this element, let's say you're doing some programming, you need to realize a very unexpected behavior for this element. And the unexpected behavior is the following. If I have a distributed load or a distributed body force on the element, and I want to take that load and distribute it as nodal forces on the nodes of the element, you'll find the components on these nodes are in the same direction as that load, but the components on the vertices are in the opposite direction. So the sum of forces, of course, will will be equal to the resultant of rho B2A and rho B1. So the sum of forces is okay, but for some reason, and we'll talk about it right now, the corresponding, so the rho B1A, the corresponding forces that would be equivalent to applying rho B1A to the whole object is equal to positive. So this, if I call this F, 1/3, 1/3, 1/3, and 1/3. So you have an extra third, and this extra third is input as a negative or in the opposite direction on the vertices. The node forces have different So notice that some node forces have different directions. From the direction of rho B1 and rho B2. So you're applying the horizontal force in the positive direction, and the equivalent nodal force is in the negative direction. Now why is that? That's because of the energy equation that we're using, or the virtual work equation. So what does the virtual work equation say? Well, the virtual, or how did I use the virtual work equation to obtain this force? So basically, what we're saying is, I want F1 multiplied by U1 star, and this is F1, is equal to the integral of rho B1A multiplied by U star dV. I want the force that I need to put at this node so that it's equivalent to the integral of rho B1 multiplied by U star when the element is displaced in this manner. Only this node moves and the rest are zeros. I have a force here, rho B1, distributed, and I want the equivalent force on node 1. The equivalent force that would produce the same virtual work. The equivalent, it turns out that this is negative. The work done by this distributed load during the application of this displacement is negative. Negative because, in fact, this area has moved in the positive direction, but this whole area has moved opposite to rho B1. Because this whole area has moved opposite to rho B1, the actual magnitude of the work is negative. And so the equivalent force here is negative. Just to use it because we're using that virtual work equation. So, in other words, the equivalent forces that would produce the same virtual work equations when you apply. what we're trying to do is the following. We have U star, rho v, integrated over the volume, and instead of U star, we want to replace this with the sum of Fi ui star. So basically we replace this distributed body force multiplied by this distributed U star displacement with equivalent forces on the nodes multiplied by this ui star, and that's when it turns out that for this particular loading and for this particular U star, this horizontal displacement, this work is negative, and so that's why F1 turns out to be okay. So the extension to 3 dimensions is just straightforward. The 3-node triangle is extended to the tetrahedron, and the properties of the 3-node triangle are inherited by this tetrahedron. So it's also constant strain shape. It's 4 nodes. The nonlinear version is obtained by adding 3 mid-side nodes, and the nonlinear version here is obtained by adding mid-side nodes here as well. The 4-node quadrilateral is extended to the 8-node brick element. And the nonlinear version is obtained by adding mid-side nodes. And so 4 nodes, so this becomes, this is the linear. The nonlinear has 8 nodes. The nonlinear has 20 nodes. The nonlinear has 6 nodes. And the nonlinear here has 10 nodes. Now there's also wedge elements, but the wedge elements are just used for wedge elements are used for areas cannot be modeled, that cannot be meshed. By either. Like wedge elements are not very good, so I'm not going to talk about them. So try not to use any wedge elements. Okay, so in general, you can invent whatever element you want. You just come up with the nodes, define the nodes, define whatever shape functions you want, define whatever displacement that element can have. But there are some requirements for these shape functions. And the elements that we introduced already abide by those requirements. And the first requirement is isotropy. Now, of course, depending on your application, if you have a very specified application, you don't need isotropy, but if for a general all-purpose FEA, you want your element to not favor a direction. So you want, if this, so you want your displacement to be isotropic in both directions. So you want both the horizontal displacement and the vertical displacement to have the same form. And the reason is because if you change your orientation, if this is x1 and this is x2, if somebody else considers this x1 and this is x2, they need to come up with the same results. So the elements should not favor a direction. The element should also be able to model rigid body motion and constant strains. Rigid body motion is represented by this constant number in your displacements, and constant strains is represented by those constants in your shape functions. The shape functions that we introduced guarantee that we're able to model rigid body motion, and that was the purpose of the question in your midterm. The shape functions that you have, the sum of ni at any point is equal to constant, which means u can always be equal to a constant, and this will be equal to 1. Is all can be equal to a constant multiplied by 1. And so, able to model rigid body motion. Now the last requirement, which is very important for the next section, is element compatibility. What does element compatibility mean? If I put two elements next to each other, I want the displacement of the element here and the displacement of the element here as I get closer to each other, as I approach both sides, the displacement should approach each other. Now, how is this achieved? This is achieved by the following. This is node 1, 2, 3, 4, 5, 6. So basically I don't want any gaps. As the element deforms, I don't want any gaps between the elements. As the object deforms, I want no gaps in the structure. So let's call this point A. The displacement at point A is function of U1. It's an average of U1, U2, U3, and U4. It's a weighted average. It's a weighted average of U1, U2, U3, U4. Because it's equal to N1, U1, plus N2, U2, plus N3, U3, plus N4, U4. It's a weighted average according to how far I am from node 1, 2, 3, and 4. The displacement at point B for element 1 is equal to function of U2 and U3 only. Because this is equal to N2, U2 plus N3, U3, and N1 and N4 on this line, when we made those shape functions, were equal to 0. So N1 and N4 right here were equal to 0, which means the displacement here does not get any contribution from node 1 or node 4. The displacement here is only a function of node 2 and node 3. U, B, if I look at point B on the other side, this is also a function of U2 and U3. It's equal to N2, let's put star, U2 plus N3, where N2 and N3 star are shape functions of element 2. Which tells me that this element is, these elements, if I have a domain made out of these elements, it will be that the elements will be compatible, and by compatible we mean that the displacements on the sides will be the same. The displacement of any point from one element on one side will be equal to the displacement on the element on the other side. Now, let's ask this question. Is this setup compatible or not?
Yes.
Okay, so who says yes? Two. I heard, I didn't see any hands. Who says no? Okay, so 3. So this setup is not compatible. So this is. So why is this setup not compatible? This element can only deform, keeping its sides straight. This element deforms by having its sides curved. So for example, I can have curve. So let's maybe give the elements different colors. These are linear elements when they deform. This node gets here, let's say this node stays here. And this is the new shape of this element. The nonlinear element will have this shape. Which means you get gaps right here and gaps right here. They're not compatible. Now, of course it's up to you. This is all approximation. If you model something like this, you just need to be aware that you have, the mesh will look fine. You're not going to see curved lines. But you need to realize that these are incompatible elements, and this is an incompatible configuration. And there are incompatible elements that are used for specific applications. And if you look at in the types of elements in Abacus, you're going to find incompatible elements. I've never used them, but there are people who use them for specific applications. They need this incompatibility for some reason. So basically, incompatibility is almost like saying the following. We're using C0. What does C0 mean? It means this is the displacement. I'm using compatible elements, which means right at the interface, the displacements are the same. That's compatibility. You, perhaps, for some reason, would like to model something using an approximation that looks like this. This, if you model elements that behave just having constant displacements on the element, or constant pressure, I mean, depending on what you're solving for, these are incompatible. If you will, the constant strain triangles, for example, like all our finite element the finite element models, all the finite elements that we use are incompatible when it comes to the strain, because the strain is not continuous. All right, we'll give you guys 5 minutes. Any questions?